Good morning or afternoon, evening, whenever you're watching this. It is morning for me while I am recording this. This is a video where I work through some of the check your understanding questions for my first block, Algebra 2, Unit 5, check your understanding questions on higher degree polynomial functions. That took me way too much effort to remember all those details, but here is the thing I'll be working with today. I'm going to turn my video off and I will just be narrating as I work through a handful of these problems. And so I'm going to pick one or two from each. There are already solutions on the second page if you need to work through that. So with this first check your understanding set, this is more built off of the last unit to help students practice who need to practice with these ideas. And so we're going to work on sketching graphs by hand using the factored form. And so I'm going to start here with h of x in the medium section. And so if I want to sketch out this function, I know that I need to graph each of my factors. Y equals 2x minus 4. That has a y-intercept of -4 and a slope up of 2 to the right 1. Up 2 to the right 1. You can also take the time to just do your y-intercept and do your x-intercept, right? So we know that if we want x-intercepts, we set our function equal to 0. And I'm going to go ahead and note that that's 2x minus 4 times 2x minus 4 since it is being squared. And so I actually have that line twice, but I'd also bring that up because that means 0 equals 2x minus 4 using my zero product property and x equals 2, just like we see in the graph. So I actually have that 2x minus 4 twice. So you'll notice I'm doing two different colors there to help me remember that. And then I have to graph x squared minus 7x plus 10. Now I already know it has a y-intercept of 10. I know it's concave up because a is positive. But I also really need the roots. And so there's a few ways to find those roots of that quadratic. I am personally going to use the area model to factor that out. And so I've got my x squared, I've got my plus 10, and I'm going to use AC. So A times C is 10. And so I need factors of 10 that add up to -7. So -2, -5 get that job done. So -2x minus 5x. And so when I factor this, vertically in this first column, got a common factor of x. Vertically in the second column, I got a common factor of -2. Horizontally in this first row, I've got a factor of x. And in the second row, I've got a factor of -5. So the factored form is x minus 2 times x minus 5 with roots. And again, you can use your zero product property, but that gives me roots of a positive 2 and a root of 1, 2, 3, 1, 2, 3, 4, 5. And the parabola is concave up. So notice this is a huge review of solving quadratic equations, of quadratic functions, linear functions, all in this one little problem. Now, I need to sketch the polynomial, and this is heavily built on last unit. And so what I'm going to do is I'm going to mark my x-intercepts and focus on positives and negatives. So when I look to the left of that leftmost x-intercept, my parabola has positive values. And then my two linear functions have negative values, right? Positive because the parabola is above the x-axis, negative because those two linears are below the x-axis, and a positive times a negative is positive. So everything to the left of x equals 2 has a positive set of y values. Then I look in between the two x-intercepts. And what I notice there is I have two sets of positive from the linear, so positive times positive. And then the parabola has negatives, and so that gives me a negative. Now, it is important to note that I don't have a double root at that x-intercept. I actually have a triple root, which is why it's going through, right? If it's a double root, it would bounce at x equals 2, but it's a triple root, so it's going to curve and go through. Notice it did not just go straight through. It curved through there, and then it comes back up to here. And so to the right, every factor has a positive value, right? So Positive times positive times positive is positive. And so I should expect that function to look something like this here. And if you use a graphing calculator to check, that is what h of x does look like. You can do similar things with k of x, and if I have time, I'm going to come back and do that as well. And so the spicy down here, again, that's extending it past what I would require. You'd have to write an equation for j of x and k of x and then do the same exact thing based on those tables. But you will notice that there are these solutions on the next page. Come on now. There we go. Okay, so moving on to the second step, you'll check your understanding questions, possible polynomial graphs and equations from features. The one issue with this is that there's infinitely many options. So I'm going to start with the medium and just give you a few examples. So number 3, degree 4, right? So if it's fourth degree, some things we would want to think about is that, hold on a second. There we go. We would need 4 zeros. There could be imaginary things like that. We probably need 3 terns or extrema. And then because it's an even degree, the positive a value, the ends need to be going up. And so we need an absolute minimum here. Okay, so let's see. I'm going to mark my x equals -3. Boop. Because I know I need an absolute minimum there. I know my end behaviors have to be like this. So let's let that be my absolute minimum. I can only have 2 x-intercepts, but all roots are real. So one option is that I come up and I do a triple root right there and continue up. That's an option, right? I've got 2 x-intercepts. All roots are real because I have a triple root plus a single root, positive a value, absolute minimum at x equals -3. That can work. I think it satisfies all those requirements. It's not the only option. Another option that you could have gone with is that you actually could have done 2 double roots here. Notice that would satisfy the same requirement of an absolute minimum here. We only have 2 x-intercepts, but all roots are real, positive a value, whole 9. The issue with number 4 is if we have a positive a value, then it has to have an absolute minimum because it's going up, but we have an absolute maximum allegedly. So those two things are contradictory. That cannot work. So that's why number 4 is impossible if you look on the next page. I'm going to pick one more, say number 6. So I have x-intercepts at -5, -2, 1, and 3. So that's only 4 x-intercepts. So that means we got to have some double roots or a triple root or even some imaginary roots. And I know it's got to have a negative a value. End behavior is the same and they're both negative, so that can work. So 1, 2, 3, 4, 5, -2, 1, and 3. So maybe something like this. Notice we got 2 double roots in there. That gets me up to 4 zeros. Ooh, it's got to have a y-intercept of -4. So let's see how I can make that work. 1, 2, 3, 4. So -4. All right, so there's an option. Again, lots of other options. That's just the one that came to mind. Down here, let's see. Number 6. Oh, I even screwed up on number 6 on the solution key. That's my bad. Notice I missed the y-intercept of -4. So that would be something I would have to correct for the future. All right, so moving on to the next, check your understanding. Identifying end behavior and possible number of extrema and x-intercepts without a calculator, right? So what I would want to notice here is I'm going to do number 5 and number 6 because there's a little bit more going on that's important. I would need to notice in number 5 here that term has my degree. So this is 6th degree. And so, and the leading coefficient is positive. So the end behavior is going up like this. And so as a result, the end behavior would be as x goes to negative infinity. So as we go to the left-hand side, y goes up to infinity. Right-hand side, as x goes to infinity, so going to the right, y is going up to infinity. Notice I didn't even find the middle because I don't know exactly what the middle looks like, but I do have all of that information just based off of the degree and leading coefficient. Also, I know from what we studied in class, the maximum number of extrema is n minus 1, but extrema come in pairs. And so the number of extrema could be 5 or 3 or 1. Let's see. Final thing, x-intercepts. So the number of x-intercepts could match the degree, so 6, but x-intercepts always decrease in possibility by 1, so it could be any of these options. And with even degree, because the end behavior is in the same direction, they could even have 0 x-intercepts. Okay. And so that's all of that in behavior, possible number of extrema, number of x-intercepts, all based on degree and leading coefficient. Number 6 here, I was actually a little tricky, and I can't remember if I did this intentionally or not, but I would point out that those two terms are like terms. If you simplify that, that comes out to be a positive 2x to the fifth. So it is fifth degree, but we do want to notice that that is a positive leading coefficient. Okay. And so the end behavior overall, this graph is, or this function is increasing. And so that's roughly what my end behavior would look like. So on the left-hand side, that's this arrow down here. X is approaching negative infinity, and y is also going down to negative infinity. Right-hand side, that's this arrow up here. X is going to the right, or infinity, and y is going up to infinity. Um, The spicy here, same exact instructions, except I do want students recognizing, hey, what's possible graphs, right? So there's lots of options just based on leading coefficient, possible number of extreme and possible number of x-intercepts. And so if you look down at the solution, I just gave an example for each. So for number 8, I got 1, 2, 3, 4, 1, 2, 3, 4, 5, 6 zeros in those 5 x-intercepts. I could have made some of those imaginary, anything like that. And that's all based on this degree here. It's going down because of that idea of a negative leading coefficient. Oh, I totally forgot on this previous one to actually talk about um, the number of extrema and the number of x-intercepts. But you can see them here, similar as before. Degree minus 1 gives me my maximum number of extrema at 4, but they come in pairs, so it could be 2 or 0. With odd degrees, it's important to remember that they go in opposite directions, so they don't have to intersect the x-axis a lot, but they have to intersect it at least once to go from negative infinity to positive infinity. So odd degree always have to have at least one x-intercept. Okay. Let's see here. So identifying types of polynomials. So you use the graph to identify what type of function is shown. A couple of things to notice. End behavior is the same down here. So it's got to be even degree. And I've got one x-intercept here and one x-intercept here, but that's going to be a triple root. So even though I only have one extremum, right, this relative max up here, I do have 4 roots, which that's okay. That can match that extrema because remember the maximum number of extrema is 3, but it could be 3 or 1 extrema. And so I've got 4 roots, I've got 1 extrema, so it's probably a 4th degree or quartic polynomial. When I look at This one right here, do this one quickly. 1, 2, 3, which you gotta look real close. 4, 5 x-intercepts. So we're talking about a fifth degree, and they're all single roots. And we have 1, 2, 3, 4. So 4 extrema, opposite end behaviors, 5 x-intercepts. All of that is leading me to 5 zeros for a fifth degree. Now, this table here, this is something that caused some students trouble on the test or the demonstrated understanding. It is good to note, right, the number of zeros for my factors, but that's not the complete way to look at it because not all polynomials will have x-intercepts, right? So the first one, natural inclination, probably third degree cubic, but actually check your rate of change. I'm going to focus here. You can look at v of x, and I'll leave that to some students. I might do it quickly in a second, but I would focus on t of x, because when I look at t of x, what I instantly or quickly notice is, man, those are easy numbers to deal with. And if I'm really paying attention, in blue here, I've got a constant additive pattern. And that means here in pink, the first set of differences, I've got a linear additive rate of change. And something that we saw months ago at this point is that a quadratic or x squared has a linear additive rate of change. Looking at w of x, I actually see a very similar thing, right? Oops, that's -1 and -3. But in this case, right, it's subtracting. That's still constant additive. And so my rate of change is also a linear additive rate of change. So this is another quadratic. And so I know that v of x, that's taking a quadratic x squared and multiplying it by a quadratic x squared, even though I can't see the zeros because they're imaginary zeros for both of them. You can graph those points to see. But when I take a quadratic times a quadratic with imaginary zeros, I still get 4 zeros. Those 4 zeros gives me a fourth degree or quartic polynomial. Okay, so fourth degree or a quartic polynomial. And to me, it's just easier to look at the rates of change of the factors. Now, you can go past that. You can look at the polynomial. I know a lot of us were doing that on the demonstrated understanding, but these numbers just are bigger. And so it's easier to make mistakes, right? To go from -44 to -18, that's another thing that causes students difficulty. I think that's going to be a +26, then a +6, a -2, a -22, and a -78. Let me check that. Yeah, 78. Okay. Then a -20, -8, -20 again. Whoa, computer freaked out. -20, -30, nope, 56. All right, nothing constant yet, so I got to keep it going. +12, -12, -36. And finally, after all of this work, -24, -24. Constant additive, linear additive. So remember, that's x to the first, which makes this quadratic additive, which is x squared. Remember, those powers are increasing each time. And that makes this cubic additive, and that's my rate of change. So x squared, x cubed, and finally we get to discover, yes, this is in fact x to the fourth or a quartic. To me, it's just way easier and less likely to make mistakes if you focus on the factors. Yeah. Lots of options for each of these as well. Just write a possible standard form. So you really have to pay attention to the degree and leading coefficient. So biggest thing for me, something like this. I know it's got to have a negative leading coefficient because overall decreasing. I know it's more than likely third degree because we got two extrema. So maybe negative 2x to the third minus 4x plus 7. And if you're like, man, Mr. Kinney, where in the world did minus 4x plus 7 come from? To be honest, it doesn't matter. The only thing that matters is the highest power and the leading coefficient. And it's a similar thing even when you get to the spicy one here. I see 1, 2, 3. Now that's a double root. So that's 4, 5, and that's 6, which that should make sense that there's 6 zeros, not 5, because the end behavior is the same. And I see 1, 2, 3, 4, and 5 extrema. So the end behaviors are both going up. So it's got to be a positive leading coefficient and 6 degrees. So I don't know, 3x to the 6. Everything after that, whatever. There we go. I'm fine with anything after that. You'll notice those are very different than what I have, but that's why, or it's probably very different than what I have. Oh, did I do minus 4x to the fifth again? No, I didn't. Okay. There's many possible answers. The focus is on the degree and leading coefficient. That's why I made that note there. Here with this one, the only thing I want to point out on the mild is keep in mind, so we're assuming a is 1 on the mild here, so f of x, make sure you have f of x because it's a function, x minus 4 times, now keep in mind when it's x equals 5i, imaginary always come in pairs, so it'd have to be x minus 5i and x plus 5i and x plus 2. You can convert that to a standard form. You can get to find the extrema, you definitely have to graph it. So I'll graph that in a second. The one thing I want to focus on really quickly is something like number 6, right? So in this one, g of x, I'm going to just call it that for a different function, got x minus, now here we don't know what a is. So x minus 2 times x minus 1 times, and it's x equals negative 2 with a multiplicity of 2. So x plus 2 and x plus 2. And I don't know what a is, but I've got this extra point. And so negative 18 is my output. Negative 1 is my input. So my output of negative 18 equals a times negative 1 minus 2 times negative 1 minus 1 times negative 1 plus 2 times negative 1 plus 2. So negative 18 equals a times negative 3 times negative 2 times 1 times 1. Negative 18 equals 6a. So a equals negative 3. And so my final function would be this. And just because of the sake of room, I rewrote x plus 2 times x plus 2 is x plus 2 squared. So there we go. And then finding those extrema is just a matter of take out my calculator. X minus 4, x plus 5i. Now you could always convert this to standard form, and then you don't have to do this factored form right here if you don't want to put in those i's, because the standard form won't have those i's. And then x plus 2. Yep, definitely want to remember to think about your window settings. I don't need to change much in the X. I'm actually going to narrow it, but I'm going to go something stupid big to start here. Okay. That's interesting. Not sure why there's breaks here. I think that's just a calculator issue. But I actually only see one minimum right in this region. What? I wonder if the calculator is not liking the fact. All right, I'm just going to convert this piece to standard form. This will be x plus 25. You can take the time to put it in area model to multiply it out, but there we go. So that's why it was acting funky. So relative or absolute minimum, right? Not relative minimum, absolute minimum of negative 234.8 at x equals 1.171. Can't find that without the calculator, personally. So there we go. And you can do the same thing with each of these. With let's do one more, say number 6 here. So -3 x minus 2 times x plus 1 times, oh, x minus 1 times x plus 2 squared. Definitely don't need all that. So let's go -50 to 50. Let's see how that looks. Ah, that looks pretty good. And so remember, zooming standard, by the way, if it was here to start, you would have to change things. But there I can see things pretty easily. I can see my double root, which makes sense. Analyze graph, minimum, it's got to be in here. Analyze graph, maximum here. And analyze graph, maximum. The reason I want to do this one is I do want to remind you, if I'm looking at this, I have an absolute maximum of 9.371 at x equals 1.569. The reason that's an absolute maximum is because there are no points above that graph. This relative minimum, this relative maximum, those are only relative because for this minimum, there's y values below there, right here and here. For this, that's only a relative maximum because there are y values above it right here. And so anytime you have a turn in the graph, right? So when you have a turn, that's a relative maximum or minimum. It can also be an absolute if there's nothing above or below. And when I say turn, what I mean is this function's increasing, right? We've talked about it in classified. Draw the tangent line here and look at the slope of that tangent line. It's going to be positive. In fact, let me take a screenshot of this really quickly so I can more easily illustrate that. So here we go. So if I am drawing on here and I draw a tangent line, the slope, ooh, that is way too thick. So if I draw a tangent line in here, touch at one point, that's a positive slope. So it's increasing. Whereas if I, and then a similar thing over here, positive slope, so it's increasing. Whereas if I look at this region, right, either right here or right here, those slopes are negative. And so because that m is negative, we are decreasing. And here we are decreasing, right? Negative slopes. And it's when the function changes from increasing to decreasing, it turns that we have a maximum, right? So increase to decrease, maximum. When it changes from decreasing to increasing, minimum. And you have to figure out, is it relative or is it absolute from there? Remember, my recommendation is to write it of the value at whatever the x value is, because that's a more accurate interpretation, right? So I have that notation all the way through here and those same exact values. Okay. This is the last little section, which is good because I am running out of time. Well, I was going to do this function here, but it disappeared. Let's hope it is down here. Yeah, it is. Okay. So I wanted to do an odd degree. So I'm going to bring that up. And so if I'm going to find these intervals of increase and decrease, like it's asking me to do, I do have to graph it, right? Remember, we just talked about those extrema are when those intervals change, right? So negative x to the fifth, plus x to the fourth plus 11x cubed minus 9x squared and minus 18x. There it is. It's actually pretty good to start. I'm going to have to delete all these points because I don't need those. Just going to shift it. There we go. I'm going to analyze this because I got to find those extrema. Minimum, maximum, minimum, and maximum. I'm going to go into the settings real quick and change that float to a 2, just so there's less decimals. It's a little bit cleaner to look at. Okay. You can definitely use more decimals for more precision, less decimals for less precision, at least one decimal I would recommend. And so I'm going to do the same thing where I take a capture the page. Let's do that. I'm actually going to, there it is. I'm going to delete that. I'm going to post this in. And so this allows me to more clearly indicate, all right, so we are talking about decreasing in this region. That's not showing up super great. The slope of the tangent line here is negative, so that's decrease. Notice color coordinating can be really helpful. Then after that decrease, we see increase, which is why we have a relative minimum here. And then after that increase, we see a decrease in this region. Again, when it stops increasing, starts to decrease. That's why we have a maximum. After that decrease, it increases. And finally, after all that, it decreases. Now, when we do our intervals, I need you to remember that and so again, I'm just basing this on slope of that tangent line. But when we do intervals, it is domain intervals. The most common issue that students run into is they put y values. But when I look at my first set of intervals here, that function starts decreasing. Where from? Negative infinity. It starts to decrease there. Where does it stop decreasing? At that relative minimum, at the domain value, negative 2.4. And so keep in mind that we use those parentheses because the slope of the tangent line at minimum and maximum is 0, so it's not increasing or decreasing. After that, it increases. Where? It starts at that negative 2.4 at that relative minimum. Where does it stop? At, notice how I keep saying at, the x value, negative 0.53, this relative maximum. Then we can see it because I've already color-coded it. Next section is decrease, and it picks back up at that previous, or at that relative maximum of negative 0.53. Really strong evidence here is just noting that these are the relative extrema because that shows an understanding that extrema are where these intervals change. And so it goes now from increasing 1.1 to 2.6. And we finally end with a decrease from that x value of 2.6 to infinity. I think I got all those details correct. I don't think I made any mistakes, but I hope this video was helpful as you study for that unit test that we have on Wednesday. Thank you very much. And I guess I need to stop recording.